Hello dear students, in the previous session we were discussing a lemma which need to prove in order to prove open mapping theorem. The lemma statement says that let B and B prime be Banach spaces and T a continuous linear map of B onto B prime. That is, they have given a continuous linear mapping from B to B prime where B and B prime are your Banach spaces, right? So we have to prove that image of each open sphere centered at origin B contains an open sphere centered on the origin B prime. That means we have to prove that open sphere centered on the origin B prime is, we denote that as SR prime, where R is nothing but the radius of your open sphere. This is contained in the image of each open sphere centered at origin in B. So this is contained in image means it will be T of, right? So T of SR. Here you can observe this is SR prime and this is SR. Why? Because SR prime is with respect to the Banach space B prime, whereas SR is the open sphere with respect to the Banach space B. So these are all the things we supposed to prove. For that, initially we have discussed some of the case, that is if SR and SR prime are open sphere centered at origin and radius R in B and B prime respectively, I can denote my open sphere SR and SR prime in this way. Using this, we concluded that SR can be rewritten as R into S1. So if I want to write it in the form of image of open sphere, it will be T of SR is equal to T of R of S1. So I can write T of SR as R into T of S1. Why? Because T is linear, right? These are all the initial conditions which we used. Now I will continue with the next part. Till here I have already proved in the previous session. That is, first we have seen that y0 is an interior point and that belongs to T of Sm, right? This is what we have seen in the previous session using Bayer's category theorem. Then we just construct a mapping f from B prime to B such that f of y is equal to y minus y0. Using this, we have proved that origin is also an interior point of T of S1 whole bar. Right? After this, we just move to the next part of the proof, that is, we are supposed to prove that S epsilon closure is a subset of T of S1 whole closure. Sorry, I will rewrite it once again. S epsilon dash is subset of T of S3. Here 3 denotes the radius of the open sphere. Okay, epsilon is some positive integer. It may be 3, 4, 5. You can consider any value for your epsilon. We supposed to prove that open sphere centered at origin is contained in your image of each open sphere. So they have not mentioned about the radius. That's why arbitrarily we have chosen the radius. Okay. So in the previous session we concluded that we obtained a sequence say xn in B such that your norm xn is less than 1 over 2 power n minus 1, and we have defined this in the form of norm y minus y1 plus y2 plus so on up to yn, which is less than 1 over 2 by n. That is, we can write yn as t of xn. We have seen all these things in the previous session itself. So for xn I have defined Sn as summation I is equal to 1 to n xi, right? So we know that xn is some sequence and we defined our xi in the form of Sn. Since xn is a sequence, from the definition we can consider for n greater than m, we have norm Sn minus Sm will be equal to norm summation I is equal to 1 to n xi minus summation I is equal to 1 to m xi, right? So this is nothing but summation I is equal to m plus 1 to n. So first if I expand this summation, since it is I is equal to 1 to n, here it is I is equal to 1 to m, till m terms it will get cancelled. So from m plus 1 you will get the summation part, right? So this is xi, norm Sn minus Sm is equal to summation I is equal to 1 to m plus 1 to n xi. So now obviously if you expand this summation, this will be less than or equal to norm x m plus 1 plus norm x m plus 2. It will continue so on plus up to norm xn, right? It is just that we are expanding our summation and using the properties of norm. I can, if I split this expansion, I will get the inequality. So now we know that norm xn is less than 1 over 2 power n minus 1. Using this here, I can write norm Sn minus Sm will be less than 1 over 2 power m plus 1 over 2 power m plus 1 plus 1 over 2 power m plus 2, so on up to 1 over 2 power n minus 1. So if you observe this part, using geometrical progression, you can write this as 1 over 2 power m into 1 minus 1 by 2 power n minus m divided by 1 minus 1 by 2. We can write this using the formula Sn is equal to a into r power n minus 1 by r minus 1. You can check that, okay? So now as m tends to infinity, as m comma n tends to infinity, the whole value will become 0, right? So now your norm Sn minus Sm tends to 0 as m comma n tends to infinity. We can write this. From this I can conclude that Sn is a Cauchy sequence in a complete space B, right? Since norm Sn minus Sm tends to 0 as m comma n tends to infinity, we can conclude that Sn is a Cauchy sequence in a complete space B. So there exists a converging point, say x, which is also in B. I can write that as limit n tends to infinity Sn is equal to x. Now I can rewritten this as, if I choose norm Sn, this will be equal to norm summation I is equal to 1 to n xi, right? If you expand this, you will be getting, with this whole term will be less than or equal to norm x1 plus norm x2 plus so on up to norm xn. So we know the value of norm xn. Norm xn is nothing but 1 by 2 power n minus 1. Using this, your norm Sn will be less than 1 plus 1 by 2 plus 1 by 2 square plus so on up to 1 by 2 power n minus 1. Again use the geometrical progression formula. You will be getting this is equal to 1 minus 1 by 2 whole power 1 minus 1 by 2 in power n divided by 1 minus 1 by 2. Right? So again you can simplify this as 2 into 1 minus 1 by 2 power n. Obviously this term will be less than 2. Right? So now our norm Sn is less than 2. Okay, so if norm Sn is less than 2, I can write that norm x is equal to norm limit Sn, and this is equal to limit n tends to infinity norm Sn, and we know that norm Sn is less than 2, so this whole term will be less than 2, also it will be less than 3. Obviously it is less than 2, since in order to prove the given thing, we are considering radius 3, right? For that purpose, I have written this is 2 is always less than 3. Okay, so this implies x belongs to S3. S3 is nothing but your open sphere with radius 3. There is a point x which is in the open sphere SR with radius 3. Okay, so this is nothing but x is equal to limit n tends to infinity Sn implies you that x is equal to limit summation I is equal to 1 to n xi. So this is nothing but, since we will write here it as limit n tends to infinity, I can write summation I is equal to 1 to infinity xi. We need to prove that it is contained in the image, right? So for that, let us operate t on both sides. You will be getting t of x is equal to summation I is equal to 1 to infinity t of xi. So we have already seen that yn is equal to t of xn. So t of xi will be yi. We can write this as summation I is equal to 1 to infinity yi, as t is continuous. So now t of x is equal to, I can write this as limit, if I expand yi, I will be getting y1 plus y2 plus so on up to yn. Here it is limit n tends to infinity, right? So this whole thing will be equal to y. This is from 10, which is our equation number 10. You can observe here. From this I can say that y1, y2, y3 so on, limit n tends to infinity y1 plus y2 plus y3 so on up to yn can be equal to y. So our y is equal to t of x and norm x is less than 3. Therefore, y belongs to t of S3. Right? Now, that implies you that initially I have taken the open sphere as S epsilon prime, since y belongs to S epsilon prime, and this implies y belongs to t of S3. This is what I have proved now. So from this we can conclude that S epsilon prime is a subset of t of S3. Right? This completes your proof. What all the things we have done in order to prove this theorem? First we constructed open sphere for B and B prime. Right? Using that we proved that SR can be expressed as R into S1. So for transformation t of SR will be equal to R into t of S1. T of SR is nothing but the image of open sphere SR in the space B, right? Then we used the Bayer's category theorem. Using that theorem we concluded that T of SM closure has an interior point, and we defined that point as some y0. So y0 belongs to T of SM. We used this, that means I have proved this part in order to show that origin is also an interior point. Right? Why we have to prove this one? Because in the statement they have mentioned that open sphere at origin, open sphere centered on the origin. So for that, first I have to prove that for origin case also we have an interior point. For that purpose we used this. We proved this part. Okay. Then we just extended our proof to prove the actual part, that is S epsilon prime is subset of T of S3. Here it need not to be 3, you can consider 4, 5, 6, anything. Anyhow, while considering the Cauchy sequence, we will prove this part, right? Limit norm Sn is less than 2, so this is obviously less than 3, less than 4. Even if you take in a general form, say epsilon, you can do that, no problem in that. Okay, for our simplicity I have taken that as 3. So this is all about this theorem. Now using this theorem I will prove open mapping theorem. Okay, first let us see the statement of the theorem, then we can prove this. The statement of open mapping theorem says that if B and B prime are Banach spaces and if T is continuous linear map of B into B prime, then we have to prove that T is an open map. Okay, so we have T from B to B prime. This is continuous linear map. Our aim is to prove that T is an open map. So in order to prove T is an open map, first I will consider one open set in B, say G. Okay, let us consider G as an open set in B. So if I prove T of G is open, then that is sufficient to say that T is an open map, right? So what we are doing, first in order to prove T is an open map, first I am considering an open set in B. Then if I prove T of G is also open set, then that means that T is an open map. Okay. So now let us consider a point, say Y, which belongs to T of G. Then there exists a vector x in G such that Y is equal to T of x. So consider a vector Y in T of G. If we have an element in the image, then obviously in the domain I will be having one more element, say x. There is a mapping from x to y, so I can write in this form, y is equal to T of x, right? So now since G is open, we have a point x in G. This implies that there exists an open sphere, say S of x comma r in B, such that this S of x comma r will be a subset of your open set G. This x is nothing but I can read S of x comma r or S of x comma r as open sphere centered at r, centered at x with radius r. This is how we read. If you have a center point at origin, then you will just write it as SR, right? Other than origin, if we have any other centered point, then I can consider that as S of x comma r. So if it is at origin, we can write that as r into S1, right? Similarly, if we have some other point as origin, I can represent S of x comma r as x plus SR. That means SR is a open sphere centered at origin, right? So if the origin point is somewhere other than, if the center point is somewhere other than origin, then it will be the point X. So you can add that point to your open sphere SR, right? So I can express S of x comma r as x plus SR. So now I can write S of XR is a subset of G, and we know that S of x comma r is equal to x plus SR. Call this as equation number 1. So now if S of x comma r is subset of G, means we can say that x plus SR is also a subset of G, right? So this implies x plus SR is also a subset of G, and call this as your equation number 2. Okay. From your previous theorem, that is from the lemma, I can say that there exists one more sphere, open sphere, say SR1 prime in B prime, right? Such that SR1 prime is subset of T of SR. This statement is exactly using from your previous lemma. That is, if B and B prime are Banach spaces, and if T is a continuous linear map of B onto B prime, then the image of open sphere centered at origin in B prime contains an open sphere in B, right? Using that statement, I can write this. So now we have S prime R1 is a subset of T of SR, right? So just operate y on both sides, you will be getting y plus SR1 prime is subset of y plus T of SR. What is y? Y is nothing but T of x, right? So now I can write this as T of x plus SR is subset of T of G. Because initially we have seen that y belongs to T of G, right? Using that, I can write y plus T of SR as T of G. Okay, so since T is linear, this is nothing but T of x plus T of SR is subset of T of G. Again, I can write this as T of x is nothing but y plus T of SR is subset of T of G. Again, using equation number 3, y plus SR prime is subset of y plus T of SR, and this is subset of T of G, right? So from this you can write y plus SR1 prime is subset of T of G. So we can write y plus SR1 prime as S prime of y comma R1, where y is the center point and R1 is the radius. This is subset of T of G. So we have shown that for any y belongs to T of G, there exists an open sphere, and that open sphere is S prime y comma R1 here in B prime, right? This is an open sphere in B prime, such that your S prime of y comma R1 is a subset of T of G. So open sphere is subset of T of G, means this implies T of G is open set. Don't get confused in this step. From this we are just operating y on both sides. Since SR1 prime is subset of T of SR, I can write this as T of x plus SR, and this is subset of T of G because y belongs to T of G. So since T is linear, I have taken T of x plus T of SR, and this is subset of T of G. So what is T of x? T of x is nothing but y. Y plus T of SR is subset of T of G. Right? So from your equation number 3, y plus SR1 prime is subset of y plus T of SR, and this is subset of T of G. So obviously this will be subset of T of G. This is nothing but, using the definition of open sphere, I can write this as S prime of y comma R1. This is y prime because this is an open sphere in B prime. Right? This is subset of T of G. Since y belongs to T of G, and that implies there exists an open sphere S prime of y comma R1 in B prime, we can say that our S prime of y comma R1 is subset of T of G. Since it is an open sphere and open sphere is subset of T of G, I can say that T of G is an open set. So this is how we prove this theorem. Now take this as an assignment. You have to prove uniform boundedness theorem. This theorem is an assignment for you. In the next session, I will continue with the next topics. Thank you.